Hey guys, I'm Shubham, and in this video we will model a mass spring system in MATLAB. The videos will be in two parts. In the first part we will be discussing the undamped oscillation of mass spring system. In the second part we will be introducing damping to this system. There are three cases for this mass spring system. The first case is the spring at rest, where there is no mass attached to it. In the second case, we have attached some mass to the spring and we notice some stretching due to it. However, the spring is still at rest. Finally, we provide some stretching to the spring and set the spring in motion. So these are the three cases for the mass spring system. We will be discussing the third case, since the first two cases do not have any kind of motion. Now let me introduce some assumptions. So I'm assuming that the mass of the bob is m. The spring constant has a value k greater than 0. Acceleration due to gravity is 9.8 meter per second square, and the length to which the spring is stretched is y. We also have some equations like Hooke's law, where force F is equal to minus k times y. The motion of the system over time t is given by my double dash is equal to F1 is equal to minus k times y. The equation has been obtained using Newton's second law of motion. The equation here is an ordinary differential equation, and upon solving it, I get y over t a cos omega naught t plus b sin omega naught t, where omega naught is square root k by m. Now that we have some equations, we will use MATLAB and check our results. We should be getting a graph of simple harmonic motion. So let's switch to MATLAB and then model our mass spring system. The first part of the code will be the initialization condition. I'm assuming the weight of the ball to be 98 newtons. The spring constant is obtained by dividing weight of the ball by stretched length of the spring, which I am assuming to be 1.09 centimeter. The acceleration due to gravity is equal to 9.8 meter per second square. Mass of the ball is weight by gravitational acceleration. Omega naught is given by square root of k by mass. F here is the natural frequency, which can be obtained by dividing omega naught by 2 pi. So nothing fancy here. We have just used the equations that we saw earlier to set up our model. Now the second part of our code is very important. I am assigning yt here as a symbolic function. Then I am doing the differentiation of y and storing it in the variable dy. After that, I am assigning the ordinary differential equation which we obtained earlier by Newton's second law of motion to the variable ODE. I'm also introducing the initial conditions y0 equal to 0.16 and y dash 0 equal to 0. The initial condition was the reason why we did differentiation of y earlier. I'm using dsolve function of MATLAB to get a solution to our ordinary differential equation and simplifying the equation. Finally, I am assigning time t equal to 0 to 10 seconds, with each step being of 0.01 seconds. Remember to convert the symbolic value of ysol to a double data type, otherwise the plot function will show us an error. So let's run our program and check the results. The output graph shows that indeed the system has harmonic oscillations. In the next part, I will introduce damping to this system. I will also discuss the three types of damping and will plot the model for all the three cases of damping. Before going further, I would like to highlight that only 8.7% of our viewers are subscribed. If you love our work, then show us your support by subscribing to our channel. Now let's introduce damping to our system. So I will be introducing a damping force F2 is equal to minus cy dash, and this force will be added to our previous system. Here c is the damping constant. New ordinary differential equation will become my double dash plus cy dash plus ky is equal to 0. Now this can be physically introduced by connecting ball of our system to a dashpot, which looks something like this as the scientific diagram, and this in a real sense. The new ordinary differential equation can be represented as a quadratic equation by assuming lambda to be y dash. So lambda square will be y double dash, lambda will be y dash, and then we divide the whole equation by m. The roots of this equation is minus alpha plus beta and minus alpha minus beta, where alpha is c by 2m and beta is 1 by 2m square root c square minus 4 times m times k. Depending upon the value of c, there are three cases of damping: overdamping, critical damping and underdamping. On solving the ODE for all three cases, we get the following result. That is, for overdamping, the solution of ODE is this. For critical damping, the solution of ODE is this. And for underdamping, the solution of ODE is this. Underdamping is an interesting one, as here beta becomes imaginary. So beta is equal to I times omega star, where omega star is 1 by 2m square root 4 times m times k minus c square. I would like to highlight that when t approaches infinity, the value of y over t approaches 0, or we can say that the system comes to a rest in all the three cases. Okay. Now let us introduce these changes in MATLAB and check our results. So I am not doing much of a change in our codes, except that I have introduced three constants: C1, C2 and C3. These constants are damping constants. I have also changed the ordinary differential equation to introduce the new terms. These are the three ordinary differential equations for overdamping, critical damping and underdamping. Necessary codes have been introduced to get solution of all the three ordinary differential equations. Finally, I am plotting these graphs of the ordinary differential equations. Now let us run our program and check the result. We can see that blue line is representing overdamping, red line is representing critical damping and orange line is representing underdamping. This part is what I was talking about, that all the systems comes to a stop for all the three cases of damping. I hope that you were able to follow along and understand how we can model the free oscillations of a mass spring system. Thank you for watching this video. Do like this video if you found it helpful. If you have any queries, post them in the comments or get in touch with us. Follow us on LinkedIn, Facebook and subscribe to our YouTube channel. Education is our future, MATLAB is our feature. Happy MATLABing!